So yeah, this is some work I did with Ryan over the past year. Yeah, so I guess to get started, what is the Hamming nearest neighbor problem? It's this problem of you're given a set of n database points of dimension small d, and we want to do some kind of pre-processing of d so that later when we're giving a query vector q of the same dimension, we can answer this question of which was the database point that we were originally given with smalling Hamming distance to the query point. So you can tell this is a really important problem throughout computer science. It comes up throughout searching things and error correction. And with this in mind, there's this really unfortunate lower bound that's called the curse of dimensionality sometimes by Barkle and Rabbani, that basically only trivial solutions to this problem work. So either you solution where you at the beginning you store all the answers to all the possible queries and it takes 2 to the d space, or the solution where on an input query you just compute all the Hamming distance and it takes about n time. So basically there are no great things we could do for this problem. But sort of since it's so important, people have come up with sort of ways around this curse of dimensionality. So a big one is to look for approximate solutions. So instead of finding the nearest neighbor in the Hamming distance, you want to just find one which is within an epsilon factor of optimal. And this work on these approximate solutions has had lots of beautiful results. Big things like hashing and dimensionality reduction came out of here. But unfortunately, Andoni and Petrascu still showed that there's this curse of approximation instead of curse of dimensionality that comes up here. And I think this is in the cell probe model where you're given a constant number of probes per query. You can show that you still need exponential and epsilon space to solve this problem. So there's still some big exponential lower bounds here. Another sort of way around this problem that's become popular pretty recently is to study this planted version of the problem, where instead of sort of looking at the worst case problem, you're instead given that all the vectors are uniformly random 0, 1 vectors, except there's one planted pair of vectors with Hamming distance much smaller than you would expect. And actually, Greg Valiant a couple of years ago came up with a really neat n to the 1.62 time algorithm for this using some fast matrix multiplication tricks. Which is especially neat because the running time is independent of what the dimension of the vectors ends up being. But nonetheless, I guess we wanted to focus on the exact original problem. And we instead focused on sort of a natural offline version of the problem. So a batch Hamming nearest neighbors problem. So here, you're given the set of n database points in dimension small d again, and you're also given a set of q of n query points all at once. And you want to find the Hamming nearest neighbor of each of the query points from the database D. So we basically want to answer n of these queries at the same time. And this is a nice problem to consider because sort of the lower bounds I talked to you about before don't apply anymore in this offline setting. But nonetheless, previously best known solutions to this were still the trivial ones. You either build a table of all the possible answers for D and then just look up everything in Q, or you compute the Hamming distance of each of the pairs in n squared times D something time. So I guess our big result that we got on this problem is this. So we basically, if we're solving this batch Hamming nearest neighbors problem, in dimension D is c log n, and c can be a function of n, but it's probably easiest to think about it as a constant or a log or something. And in a sense, I think log n is sort of the interesting dimension to consider this problem in. Then we can solve a batch of n Hamming nearest neighbor queries on D in 2 to the n minus 1 over order c log squared c time with high probability. So when c actually is a constant, when the dimension of the vectors is log n, then this is a truly subquadratic time algorithm. For like given the constant, there's an epsilon greater than 0, such that this runs in 2 to the n to the 2 minus epsilon time. And this is the first algorithm like this that we really know of. But it improves on the trivial algorithm even when d is like order n squared over log squared n. And another really cool thing about this algorithm is that our techniques we use are really, really different from past work on this problem. So I'll tell you about this for the rest of the talk, but basically we're going to use some cool applications of probabilistic polynomials to compute a lot of Hamming distance quickly. And this is like very different from what people have tried before. And the last thing to note about this is that, well, we also prove a Seth lower bound on this problem. So what we show is that if there's an epsilon greater than 0, such that for any constant c, you can solve this in like n to the 2 minus epsilon time, that would violate the strong exponential time hypothesis. So yeah, to be really clear about this, we get that for any constant c, there exists an epsilon. But if we instead showed that there exists an epsilon for every constant c, that would violate Seth. So like with this in mind, there's like a potential limit to how well you can do on this problem. And like maybe you can't do very much better than what we got. All right, so with that in mind, I'm now going to sort of shift gears completely for a little bit and tell you about polynomials. And then at the end of the talk, we'll come back to how to use polynomials to solve this problem. So yeah, the question is, right, how are polynomials relevant at all? And the nice thing about polynomials that sort of we've seen over and over during this workshop is that you could use them to compute Boolean functions. So if you let R be your favorite ring, we're usually going to use Z or Z mod something for this talk. Then you say a polynomial P in n variables over the ring computes the Boolean function f if for each possible 0, 1 vector as input, the polynomial evaluated at the 0, 1 vector is equal to the Boolean function at that 0, 1 vector. So for a quick example, if you look at the OR function, the OR function is like 0 if all the inputs are 0 or 1 otherwise, right? Then it's equal to this polynomial P here, 1 minus the product of 1 minus xi. And you can see like if all the xi's are 0, then this is 1 minus a product of 1s, so it's 1 minus 1 is 0. And if at least one of the xi's is 1, then that term of this product will be 0. So the whole product is 0, and it's 1 minus 0, which is 1. So this polynomial exactly computes the OR function. And yeah, you can check this polynomial has degree n, and 2 to the n, I think actually 2 to the n minus 1, like monomials when you expand out this whole product here. So an important thing about polynomials for Boolean functions is that you never need to take a power of a variable greater than 1. Because since we're only substituting in 0 or 1, like x is equal to x squared when x is either 0 or 1. So in other words, we only need to look at multilinear polynomials for computing Boolean functions. So the degree can be at most n, and there can be at most 2 to the n terms. So in some sense, this OR polynomial is like as big as possible. And for our algorithmic applications later, we're going to be looking for small polynomials. So this is really bad. And like you might hope maybe we can be more clever and come up with a better OR polynomial. But it's not too hard to see that any Boolean function has a unique polynomial representation. So we couldn't do that. So I guess just like sort of in algorithms, you might look at probabilistic algorithms to speed up or use less space or something. Similarly, we're going to look to probabilistic polynomials to try to help us find smaller polynomials. So I guess we've seen this definition a couple times already too. But a probabilistic polynomial is, in addition to having like a degree parameter d, there's also an error parameter epsilon. And it's actually, instead of just being one polynomial, it's a distribution, like squiggly d over polynomials. And it computes the Boolean function f if the probability over drawing a polynomial p from the distribution that the polynomial evaluated at an input x is equal to the Boolean function evaluated at x is at least 1 minus epsilon for every possible input x. So yeah, this is really important. The probability is over drawing a polynomial from the distribution, but this is a worst case over inputs x. So I guess later on when like we need our algorithm to have a good chance of being right on any input. This property is going to be important. So let me give you an example of one of these. I'm going to tell you about a probabilistic polynomial for or over the integers, which is by these guys from 1993, like 20 years ago. So typically how you construct one of these probabilistic polynomials is you like define some randomized algorithm which produces a polynomial at the end. And then like the distribution of what this algorithm might give you defines your distribution over polynomials. So here the, I guess, randomized input to our algorithm is going to be these sets S sub I. So we'll let S0 be the set of 1 through n. And then for each I from 1 to log n, log n plus 1, we're going to let Si be the set where you start with Si minus 1, and then keep each element that's there with probability 1/2. So like S0 has all n elements, S1 will have about half of them, S2 will have about a quarter of them, and so on. Then for each of those I, we'll define this like intermediate polynomial. P sub I of x is the sum over just the j's in that set S sub I of xj. And then our probabilistic polynomial for or is going to look like this. And you can see it has some similar structure to our or polynomial from before. That's like 1 minus a product of 1 minus some things. So yeah, I guess this you can tell this always has degree like log n. So it's definitely a log n degree probabilistic polynomial. So let's see why this actually is for the or function. Yeah, so first of all, if the input is the all zeros vector, then each of these p sub i's is just a sum of zeros, so it's 0. And this is 1 minus a product of 1s, which is 0, just like we want. So what we need to show, or what I'm going to show, is that for any other input x with at least a 1 in it, this polynomial evaluated on x has at least a 1/3 chance of outputting a 1. So, and to show this, I'll show there's at least a 1/3 chance that there's some I for which p sub I is 1, because then that term in this product will be 0, and so it'll be 1 minus 0, which is 1 like we want. And so this is sort of like a really basic probability kind of argument. Like, so what's going on? At the beginning, p sub 0 of x is just the sum of all the entries of x, because s sub 0 is the whole set. So p sub 0 is just the number of 1s in our input vector. And then log n plus 1 times, we like, whatever number we have so far, we flip that many coins. And whatever number of heads we get, we write that new number down. And the question is, are we ever going to get a 1 if we do this sequence? So sort of the two bad things that can happen are, first we could start with a really big number, like the biggest we can start with is n. And then we do this the log n plus 1 times, but still at the end we haven't gotten small enough to get to 1 yet. Like we're still at least 2. But since you can tell, like since we're flipping log n plus 1 times, like the probability we don't get to 1 is at most a half, say. So the other bad thing that can happen is we do get like all the way to 0, but like at some point we're at 2 or greater, and we skip straight to 0 without going through 1. And there you can tell like if you have 2 or more coins and conditioned on getting like going to either 0 or 1, the probability that you go to 1 is at least 2/3, like some basic probability. So in total, the probability that we'll get a 1 in this sequence is at least a half times 2/3, which is a third, which is the number here. And this works for any x, no matter what the x was. Yeah, so you might be thinking, all right, this is not so great. Like we have a polynomial that only gives the right answer a third of the time, but there were only 2 choices, so that's not very helpful. But you can see that the error here is one-sided. Like if the answer is supposed to be 0, we always give 0. And if the answer is supposed to be 1, we give 1 a third of the time. So if you take like log 1 over epsilon draws from this distribution, and then just like plug them into our exact polynomial for or from before, then you can get a degree log n log 1 over epsilon polynomial that has error any epsilon that you want. So this is really good because like before our polynomial for or had degree n, and now our polynomial has degree log n. So this is an exponential decrease in the degree. And in fact, if you work over like the integers mod 2 instead, you can even get rid of this log n factor by a nice argument by Razbrov and Smolensky. So this is like a huge savings. So I guess the Boolean function that we really care about for our Hamming nearest neighbor problem is the majority function. And I'll explain more about why this is later, but sort of the intuition is that when you're computing the Hamming distance of two vectors, you're like counting the number of places in which they differ. And similarly, majority is like counting the number of ones in your vector and seeing if it's at least a half. So that's sort of the idea, but I'll make it more clear later. So the function we care about is the majority function. Yeah, just some notation, the like magnitude of x will be the number of ones in the vector x. And then the majority function is just 1 if that magnitude is at least n over 2. Unfortunately, like as I think we even talked about in the last talk, there's this theorem by Razborov and Smolensky from '87, which says that a probabilistic polynomial for majority requires degree root n log 1 over epsilon. So we definitely can't get a like exponential decrease in the degree here. The best we could hope for is like some square root decrease in the degree. Yeah, and so this is kind of unfortunate, and I guess has prevented a lot of work with probabilistic polynomials for majority in the past a little bit. But we're going to continue anyway and actually show that there is a probabilistic polynomial for majority with this same degree, root n log 1 over epsilon. So this degree will turn out to be like exactly what we want for our application. Like any bigger would have been too big, I guess. Yeah, so what was the past work on this problem? I guess, yeah, Srinivasan worked on a slightly more general problem where he was looking for probabilistic polynomials for what are called W-sum determined functions, which are determined by some weighted sum of the inputs. And if you like apply what he would get by looking at the majority function there, you get degree root n log 1 over epsilon times some polylog n factor. And that'll turn out to be too big for our application here. Yeah, so okay, so let me tell you how our construction works. And we're actually going to look at the threshold function. So its parameters by theta, and it's 1 if like the fraction of ones in the vector is at least theta. So in particular, the majority function is this with theta equals a half. So yeah, I guess the details here are very tricky, but I'm going to try to give you all the big ideas in just one slide. So we're going to use a recursive idea. So we're basically going to break into two cases depending on how close our vector is to that threshold. So how close the fraction of ones and x's to the threshold that we care about. And it'll turn out that this parameter delta here is like the how close that we'll want to look at. So the first case, if we're really far from the threshold, like not only are we past the threshold, but we're way past it, or not only are we not above it, but we're way below it, then we can do a sampling trick where you like construct a smaller vector x tilde by just sampling a constant fraction of the entries of x. And by like the Chernoff bound, you can see that this sampled vector has the fraction of ones in the sample vector lies on the same side of theta with like really good probability as the original vector did. So we can sample the smaller vector and then just solve it on like the smaller instance of the problem. And then if the fraction of ones in our vector is really close to the threshold, then somehow there's like intuitively there's not anything really great we can do. Like if we try to do something randomized, like we're so close to the threshold that we might miss a single one and like everything will go wrong. So here we're just going to use an exact polynomial that you can get by interpolation of degree like n times delta, which turns out to be root n log 1 over epsilon, for the threshold function. So we're just going to have a polynomial which is exact and is guaranteed to give us the right answer on these inputs. Okay, so we're constructing a polynomial, right? How are we going to decide which of these cases we're in? Well, we're actually going to use the same recursive idea again. If we can have threshold functions for theta plus delta and theta minus delta that we substitute in the sampled vector, which will give us a good enough idea of which of these two cases we're in. And sort of the hard part here is like maybe we're right on the border, and then which case are we going to pick? And we'll deal with this by like we'll make our exact polynomial here. like be exact for a little bit more than we actually care about, like twice the width or something like that. So that in the middle there, like no matter which of what these thresholds end up saying, we'll still probably give the right answer. Yeah, so that's the idea for our construction. And because of how you end up picking delta, you get a degree of root n log 1 over epsilon. Okay, so the question now is, how are we going to use probabilistic polynomials to compute something quickly? And the big idea is to use this lemma that Ryan proved, that basically if you have a polynomial and you divide up its inputs into like an x set and a y set of inputs, and then what you want to do is evaluate this on lots and lots of inputs. So like you have some big set of A of like x sets of vectors and some big set B of like y sets of inputs, sorry. And you want to evaluate it on all pairs of a choice of the x's and a choice of the y's in A cross B. So, and yeah, these have size n. A and B have size n. Then normally, if you just do this in the really obvious way, it would take n times. Oh yeah, we have this sort of this requirement that they're at most n to the 0.17 monomials for like a technical reason. So normally it would take n times n to the 0.17 time to do this in the really obvious way. But using a like fast rectangular matrix multiplication, you can actually get it down to about n squared time. And this like surprising speed up here is where our surprising speed up for our later problem is going to come from. Yeah, so basically, if you have a polynomial that has not too many monomials, then you can evaluate it on lots and lots of points faster than you would expect you'd be able to. So what we're going to do is use this and our majority polynomial to solve this subproblem of the batch Hamming nearest neighbor problem. So this subproblem, I'll just call it the Hamming distance problem, is you're given two collections of S vectors and an integer k. And we want to determine just whether there's a choice of one vector from each collection with Hamming distance at most k. So this is like a subproblem we're going to use for our bigger problem. So how do we do this? Well, we're going to define a polynomial for this subproblem using our majority polynomial. It's going to be a probabilistic polynomial again. And here we're going to work over f2 because we'll see like working over f2 gives us some degree savings here. So what are the ingredients of this? Well, first we'll let x1 through xs and y1 through ys be the two collections of vectors. So we're looking at there's an xi and a yj with Hamming distance at most k. And yeah, for notation we'll write xi comma j for like the jth variable of the vector x of I. So the first ingredient is that we're going to use our threshold function probabilistic polynomial we just defined for threshold value k plus 1 over d. And this will be a function on d inputs. So this is checking whether or not at least k plus 1 of the inputs to it are 1. And we'll sample it with this error, which will make the math work out nicely later. The other ingredient is going to be a uniformly random subset of the set of ordered pairs of two integers between 1 and s. And I'll explain where this comes in a second. But this is like each pair is in this set R with probability 1/2. Okay, so our polynomial is defined like this. It's going to be the sum over the pairs that we ended up randomly picking of 1 plus our threshold polynomial evaluated at the sum, like the entry-wise vector sum of x of I and y sub j. Okay, here it is again, up here. Okay, so let's see why this works for our function we care about. So first of all, yes, we're going to use this fact that we're working over f2 here. Since we're working over f2, the sum of two 0, 1 variables is 1 when they're not equal to each other, and it's 0 when they are equal to each other. So the number of 1s in the sum vector is exactly the Hamming distance between x and y. And that means that, well, assuming p is correctly evaluating the threshold function on this instance, p evaluated at that sum is determining whether the Hamming distance between them is at least k plus 1. So 1 plus that is 1. if and only if the two vectors have Hamming distance at most k. Okay, so if all of them, so if all of the pairs in our, if all of the pairs of an xi and a yj have Hamming distance greater than k, so this is the instance we're supposed to return no for our problem, then each of these terms is 0, assuming the probabilistic polynomial is correct, and so this is a sum of a bunch of zeros, and it'll always return 0. Meanwhile, if there's at least one pair where the Hamming distance is at most k, then I claim there's a 1/2 chance that this polynomial will output a 1. And to see this, you can do this trick where like you pick all the pairs in R except for the one which is actually going to give a 1 in this sum, or one of them. And then before having picked this pair, the sum was either a 0 or 1. It doesn't really matter which. So with 1/2 chance, this pair will change the value of the sum. So with 1/2 chance, the value of the sum is actually going to be 1. And once again, this is nice, like one-sided error. Like if the answer was supposed to be 0, assuming our polynomial p was correct, then we're always going to say 0. So we can amplify it just like before. And here, like it turns out, we're only going to need to take like two samples of this to get the probability that we want of success. Yeah, there's some more details about like making sure the probability p is correct is high enough, but I claim that it works out. Okay, so we now have this nice polynomial for the subproblem, and there are 2 steps left. The first is to actually get from this polynomial to an algorithm for the Hamming distance problem, which I'll remind you again, checking whether there is a pair with distance at most k. And the second step is getting from this subproblem to the problem we want to solve, the batch Hamming nearest neighbor problem, where for each of the vectors you want to find its nearest neighbor, which is like a seemingly harder problem, I guess. Okay, so let's start with the first one. And this is interesting because this is where the weird c log squared c thing is going to come from. Okay, so yeah, so if R and B are 2 sets of vectors of dimension d, they both have size n, and d is like c log n, then, and finally we're given a value k, then we can find a vector v from R and a vector u from B whose Hamming distance is at most k in time n to the 2 minus 1 over order c log squared c, or determine that none exist. Okay, how do we do this? Well, we're going to use our polynomial we just defined for this problem, right? So we first partition each of R and B into n over s groups of size s, where s is going to be this 1 over order c log squared c value. So what we do is, so we take our probabilistic polynomial we just defined, and you can see that if you look at the degree of the construction we made, this polynomial has degree root d log s. The error was like 1 over s cubed or something like this. So the number of monomials is going to be something like 2d choose root d log s. And here I'm hiding some like polynomial terms outside the binomial coefficient that don't really affect what the number of monomials ends up being. And the important thing to note here is that if we choose a big enough constant inside this like size of the group over here, then we can make this binomial coefficient be at most n to the 0.17 for any like s and d and whatever. So yeah, so in other words, this was exactly the size s we needed to make us able to use our probabilistic polynomial inside the fast evaluation technique with rectangular matrix multiplication from before. And here's the part where if the degree of the probabilistic polynomial were any bigger, this wouldn't work. Because if we had like an extra log d term here, this binomial coefficient would be too big to ever give at most n to the 0.17 monomials with like a significant saving in the size s here. All right, so using the fast evaluation, we can then evaluate the polynomial on all the pairs of groups in this much time. And then I guess this will tell us, based on whether any of them returns 1 or not, whether there's a pair with distance at most k. And then the last trick is just like, if there is such a group, we can actually just brute force to find which pair of vectors it is, because the S is so small compared to n squared. Okay, so that's the first lemma. And then the second one to actually get is we actually have to get from that Hamming distance problem to the seemingly harder batch Hamming nearest neighbor problem. And here we're actually going to use a nice fine-grained reduction kind of thing. I think maybe this exact same idea came up at the workshop a couple weeks ago. So the idea is we're going to show that if you can solve the Hamming distance problem in time t of n and d, then you can solve the batch Hamming nearest neighbor problem in time n times d times t of root n d. So we're going to do it on instances of size root n instead of size n. And the idea, it's like a partitioning thing again. We partition the set D of database vectors and the set Q of query vectors into root n groups of size root n. And then for each k from 0 up to d minus 1, we're going to go and find all the query vectors Q that have Hamming distance k from something in D, and then remove them basically. So we start from k from 0, and we go up to d minus 1. And what we do is we call our Hamming distance problem algorithm for each of the pairs of one of the groups from D and one of the groups from Q. So they're root n groups from D and root n groups from Q. So there are n of these in total. And then for each of these groups, if we find a pair of a vector u and a vector v that has Hamming distance k, then that means that v is a nearest neighbor for u. So we can remove u, say the answer for that one is k, and continue. And we'll even repeat on that group again. And if we don't, if we call to that group and they say none of them have distance that was k, we'll just continue to the next group. I guess whenever we call this for the correct k on the group containing the two vectors that actually have the smallest Hamming distance, then we should find the correct pair for our vector u. And the nice thing to note is that we'll call this d times n times, n is the number of pairs of groups, plus at most one more for each time we actually find one of these pairs in Q, which is just another n. So the total number of times we call the sub-algorithm is just order n times d. And we're calling it on instances of size square root of n instead of size n. So we get this time I wrote over here. Yeah. And then finally you substitute in the time we got for the sub-problem, and you get exactly the running time for the original problem that I told you at the beginning. Yeah, so that's about it. I guess just to summarize, these probabilistic polynomials are pretty cool because in the past they are mainly used for circuit lower bound kind of techniques, like the result by Razborov and Smolensky lower bounding the degree of a probabilistic polynomial for majority was originally used to get low depth circuit lower bounds for the majority function. But here we use it in a sort of completely different way to actually make some small computations really fast. And by combining this with rectangular matrix multiplication tricks, we can do lots and lots of Hamming distance computations in faster than you would expect to be able to. So that's really where this order c log squared t c term comes from. Yeah, and I guess I'm kind of hungry, and you guys are probably hungry, so I'll just stop now. Yeah, thanks.
There are other functions from which, if you can get polynomial, you get a better algorithm for something that's interesting?
Probably. I've been thinking about this a bit, I guess. Yeah, if there are any algorithmic problems where you can find a nice sub-computation you do a lot of times, then I think it's a good candidate for this method. Yeah.
So I suppose fast matrix multiplication is still sort of essential to get to subquadratic time, or?
Yeah, it's really the savings there that go on to the savings here. Yeah, but I guess the weird thing is that like improving rectangular matrix multiplication probably wouldn't help anymore here. Like the 0.17 in the exponent, it doesn't really make much of a difference.
Speaker again.